Everybody, we are in lecture 13 of this particular course. In previous classes, we have seen how to minimize the logic expression and get a implementation for single input cases. So, in this particular class, we shall look at multiple output minimization, and we shall see that there are very many different possibilities, and we have to weigh one option against the other, for which we need to define certain cost criteria. So, we shall begin this particular lecture by defining certain cost criteria, and then we shall look into the minimization aspect. So, the kind of implementation we had seen before, we start from there. So, this is a representation of a truth table where the mean terms are 2, 4, 5, 6, 7. Okay, this is familiar. We had already solved this particular kind of minimization problem before, and in the SOP case we have the realization where one mean term comes from here, which is A, and another mean term comes from here, which is B C prime. Okay, this we have seen before. So, in the SOP realization we have y is equal to A plus B C prime in this manner, right. And for the same truth table we can have a POS representation, for which we are having two such sum terms, one is A plus C prime, another is A plus B. Okay. Now, if you want to realize this in the form of circuit, for each of the operation we have corresponding logic gate available. So, we consider that the inverter inverted input, complemented and uncomplemented, both type of input is available. If it is not the case, we can consider it separately. So, we have a two level logic implementation. So, in this case we are having two gates, one gate is the OR gate combining A and the other A and B C prime, another gate is an AND gate which is generating B C prime, fine. And compared to that we are having A plus A or B generated by this one, A or C prime generated by this one, and this AND gate is combining these two outputs of the OR gates. Okay. So, if you look at the complexity and say that which one is more costlier implementation, of course, this one is the POS is a costlier implementation in this case. It is very clear, very evident here, isn't it? So, if you look at the number of inputs and number of logic gates that are used here. Okay. But it may not be the case so simple, we need to for more complex circuit, especially for multiple output minimization. So, for which we look at defining certain cost criteria. So, one definition is that of literal cost. So, literal cost is the number of times a literal appears in complemented or uncomplemented form in the Boolean expression. Okay. So, that is what is known as literal cost. So, if we look at the previous example, so how many times it is appearing? A, B and C prime, complemented or uncomplemented, both are both are to go as a literal cost. So, 3, right. In this case A, B, again C prime. So, 4 times literals are appearing. So, literal cost is 4. That is how the literal cost is arrived at. Next is gate input cost. So, compared to literal cost, gate input cost gives a better appreciation of the complexity of the circuit that is getting implemented. Okay. So, in the gate input cost, the number of inputs to the gates in the implementation that gets counted. So, in the previous example, in this example, how many this SOP realization, how many is the gate input cost? So, 1, 2 over here, another here. So, these are the 3, this is 3. And what is the gate input cost for this POS representation? 1, 2, 3, 4, 5, 6. So, these are 6. Okay. So, here we are not counting the inverter, NOT gate. Okay. So, if you count the NOT gate, then we get another measure one is defined by G, another is defined by get input cost including not get count. Okay. So, in each of these cases, see, one inverter will be coming here. So, this will become 3 plus 1 and this will become 6 plus 1. Okay. If we consider the inverter or if you do not consider the inverter, these are the two cases that is possible. Now, we can very quickly, without going for the diagram and getting the implemented circuit, logic circuit in place, right from the expression we can get the get input cost very easily by considering these two equations. Okay. So, if the number of terms excluding single variable term, okay, excluding single variable term because it does not require a gate, okay, is T and the number of distinct inversions is T. Number of distinct inversions means that if A bar is used in two places, it will be only counted once. A bar as literally is coming in two places, distinct inversion is required, only one inverter, one NOT gate is required. So, that is the distinct, that is defined by distinct inversion. So, if that number is T, okay, then the get input cost without considering the NOT gate count is literal cost plus number of terms. Okay. So, we can see what is the get input cost by and literal cost by from this formula. So, in this example, without looking at this gate, so literal is 3, 1, 2, 3, A, B, C prime, and number of terms excluding single variable term. So, excluding single variable term, this is a single variable term which have to exclude. So, number of term is only 1. So, 3 plus 1, 4 is the get input cost without not get count. Is it fine? Right. So, and we can count here 1, 2, 3, 4, 4 gates are there, 4 get inputs are there. In the other case, how many literals are there? 4 already you have seen, right? And how many terms are there? There are 2 terms, one sum term, and there is another term, sum term. So, 4 plus 2, 6 is the get input cost, and we have counted that 6 is the get input cost. So, that is how we can get just by looking at the expression without going for a physical realization of the or drawing of the logic circuit, we can get the get input cost. Okay. And if we want not get count additionally, in addition, then we shall add the number of distinct inversion for this. Okay. So, this is put in a tabular form here. So, this is 4 and this is 6, right, and 5 and 7 if we include the not get count. So, mostly it is get input cost that is considered in the study. So, we look at few more examples, and this realization and this realization both are equivalent. Okay. They represent same truth table. Okay. Now, we are not drawing any logic circuit for them. So, simply by the way we have calculated using that formula, we shall see what is the get input cost here. So, number of literals are 1, 2, 3, 4, 5, 6, right. So, 6 literals. So, literal cost is 6. Number of term 1, 2, 3. So, 3, right, and there is no inversion involved. So, n is 0. So, 6 plus 3, 9 is the get input cost, okay, without not get count, and with not get count is also 9 because there is no inverter used. And equivalent representation, POS representation for this is A plus B ANDed with B plus C and ANDed with C plus A. Again, number of literals is 6, you can see, number of terms is 3, right, and no inversion. So, 9 and 9. So, both are equivalent in terms of complexity, any one of them you can pick up. Okay. There are again 2 equivalent representation of same truth table, one is in SOP form, another is in POS form. Okay. Now, how we see how they are compared in terms of the cost that we have just defined. So, literal cost in the first place is 1, 2, 3 and 4, 5, 6, 6. Okay. Number of terms 2, 1 and 2, right, and inversion required A prime, B prime, C prime, so 3, right. So, get input cost without not get count, literal cost and number of term 6 plus 2, this is 8, and in the other case including not gate count is 11. And for the other one, the POS realization, we have got A prime plus B, B prime plus C and C prime plus A, 3 OR terms are getting ANDed. Okay. So, 6 is the number of literals, 3 OR terms are there, 3 terms are there you can see, right, and 3 inversions A prime, B prime, C prime are required. Okay. So, your gate input cost is 6 plus 3 9 and this is the 12. So, of course, now we can consider compare and you can say that this one is a less costly realization. Is it okay according to this definition? So, these are few more examples. So, this is they are not equivalent, just here number of terms are there 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 number of literals. So, 11 literals 1, 2, 3, 4 terms are there. Inversion B prime, A prime, B prime again and C prime, but B prime will be counted only once, distinct inversion. So, it is 3. So, that way you are getting 15 and 18 for these cases. Similarly, for the other. And when we do this, we consider 2 level implementation and there is no restriction in fan in or the kind of logic gates that is to be used. Okay. The way we actually minimize circuit in Karnaugh map or QM algorithm using Quinn-McCluskey algorithm. So, that is what we have that is what is being considered here. But if there is a restriction in fan in, if there is a restriction in say the kind of gate that you can use, then of course, this is not the way we have to calculate this one. For example, if it is asked say this expression y is equal to A B plus C D E. Okay. So, this is to be realized and the restriction put is you have to use only 2 input NAND gate. Okay. Then what is the cost? Okay. So, now 2 input NAND gate becomes 1 unit, right, and we can use De Morgan's theorem, right, successively and we can see that 1, 2, 3, 4 and 5. So, 5 2 input NAND gates will be required. Okay. So, this is the realization. So, there could be another realization, possible realization. So, we have to compare against them and depending on number of units we will pick up with the one which is less in cost. And here you see the 10 gate inputs are required, 2 input NAND gates 5 into 2 10 gates. But if you look at the normal 2 level implementation with no restriction in fan in and all, then the literal cost is A, B, C, D, E 5 and number of terms are 2. So, it is 7. So, number of gate inputs required if we go for no restriction 2 level implementation is 7, but because of the restriction we are now having 10 gates, but so and 5 2 input NAND gates used in this particular problem. Okay. Now, what is meant by 2 level and 3 level? So, let us look at one more example, I mean 2 level and more than 2 level. So, here we are realizing A B, C D and C E, A B plus C D plus C E. So, if you go for 2 level implementation, then what is the gate input cost? 1, 2, 3, 4, 5, 6 literal and 3 terms, 6 plus 3 9 and you see 9 gate inputs are there 1, 2, 3, 4, 5, 6, 7, 8, 9, 7, 8, 9, right. And what about this one? We see that if we take C common, A B plus C ANDed with D or E, this expression, then C D or E getting ANDed, okay, which is odd and then ANDed with C and then finally this is. So, this is 3 level implementation, right, and how many gate inputs are there? 1, 2, 3, 4, 5, 6, 7, 8, right. So, instead of 9 we are having 8. So, this is for 3 level implementation. So, our discussion is on 2 level implementation, the way you usually do for AND or NAND or for POS OR AND or NOR circuit. Okay. Another point here, in some of the literature you will find that the total cost another definition is given for cost, which is number of gate input, that is the gate input cost plus number of gates that are used. So, additionally number of gates that are used, that are also put into consideration which is defined as total cost in some of the literature. Okay. Now we come to the multiple output minimization problem, and we will keep this cost aspect in our mind. And what we see is that there are various possibilities. So, in one case, the first case we look at the problem where the between two functions that are to be realized, the common term is a prime implicant in both the places. So, you see these are the common terms between these two functions that are to be realized. So, B prime C is the common prime implicant, right. And of course, in this case the decision is obvious. So, if you go for individual realization, so this is what you will be doing. So, B prime C over here, again B prime C is again realized over there, and then this is the corresponding circuit which will require 6 gates, okay, 1, 2, 3, 4, 5, 6 gates, and the gate input cost for each one of them is 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. Here also you can count 1, 2, 3, 4 literal and 2 terms 6. So, 6 into 2, 12 is the gate input cost, and if you look at the total cost, I mean including the number of gates being used, it is 18. And of course, this B prime C is a candidate which can be the common term, shared term, which can be used for both the places. So, this is the corresponding circuit. In this case, to realize this part, you would need 6 gate inputs 1, 2, 3, 4, 5, 6, and to realize this part which is common, you need 4, right. So, 6 plus 4, 10, and the gate count will be total cost will be also 10, 3 for this and the 2 for the other one, so 15. So, it is very simple. In this case, we do not have any issue in coming up with the minimized multiple input solution, right. So, this is the minimized solution. Now, look at a problem where there is no common prime implicant as such. Okay. So, in this case, so F1 0, 1, 3 min terms and F2 has got 3 and 6 as min term. So, you have got these two terms. If you go for individual implementation, A prime B prime and A prime C, these are the one that are to be realized. Okay. And in this case, this is common, right, but as I said, in this particular case, this is to be realized, but this is not the term is there in the other case as a prime implicant. It is already covered by the one of the term, okay, A prime C, right. So, individually if you realize, these are the two terms and if you calculate the gate count in this case, gate count cost. So, for the first one 1, 2, 3, 4 and 5, 6, these are the term, this is the term, and for the second one 1, 2, 3, 4, 5, 6 and 2 terms 8. So, this is the gate input cost, so 14, right. And if you look at the total cost 14 and 3 gates are used here, 3 gates are used there, so total 20. Okay. But since the common term over here is to be generated, you have no choice because the other term requires it. Okay. So, there is another way you can realize it where you are not generating A prime C over here, rather this A prime B C which is generated, that is being used, okay. And in this case you have got one common term, one shared term which is being utilized by both the expression. So, in this case how does it help? So, it helps by reducing the gate count. In the first case 1, 2, 3, 4, 5, 6, 7, in the second case 1, 2, 3, right, and there are 2 terms 4, 5. So, 7 plus 5, 12, okay, because A prime B C is already generated in the first case, right. So, total is 12 and the total gate cost is count cost is 12 and this is 17. So, if you compare, you can see that you are in gain. Okay. So, it is less costly. So, it is to be realized in this manner by this expression, not by individual. Okay. Now, let us look at another example where we have got common term, right. But this common term is already part of bigger groups which is already covered. Okay. So, let us look at this particular example, what is happening over here. So, between these two, this is F1 and this is F2. Okay. So, between these two, you can see this is these two ones are the common term, right. Now, these two ones can be part of a bigger group D1. Therefore, if you go for individual minimization, this is how we will realize it, B C prime B D and A prime B prime C. So, this is this term A prime B prime C, and another one term is B C prime, which is coming from here, and the other one is your B D. So, this is the term that we are talking about. Okay. So, this is how you will get it, and for the second case, this common term can be part of a bigger group. Okay. So, this is the corresponding realization of it. So, B D prime B C A B prime D. So, this is A B prime D. Okay. Now, the issue with this is that by making a bigger group of 4, you are the ones that you are covering, it is already covered by the previous group, one term B C prime over here. Similarly, by forming this bigger group, you are covering this one is already covered by this group of 4 which is covered in the blue, right. So, there is no necessity of grouping them in that manner and generating two distinct term, right. One is B D, another is say B C over here. Rather, you can generate only one of the term, this term which is B C D, and which can be shared in both the places. Okay. If you do, does it help in any way? We can see that it helps in a manner which is depicted here. If you go for individual minimization. So, 1, 2, 3, 4, 5, 6, 7 and 3 terms 10, and similarly the other one is 10, get input cost is 20. Whereas, in this case 1, 2, 3, 4, 5, 6, 7, 8 and 3 terms are there 11, right. In the second case 1, 2, 3, 4, 5, this is already generated, and 3 terms, that is 5 plus 3, 8. So, this is 19. So, this is 20 versus 19. Okay. Similarly, if you look at the total count, including the as I said, in some measure they are considering also the number of logic gates that are used. So, this is 28 versus this is 26. Okay. So, this is a better less costly realization. Okay. So, this is what we find when the common term is a part of bigger group where the members are already covered by other prime implicants in individual cases. Okay. Now, we look at the case where the do not care is there, okay, and we see that how the do not care can be considered in the multiple output minimization. Okay. So, we have taken two examples. So, in one example you see that these are the do not cares, this is do not care in for function 1, and this is do not care for the function 2. Okay. Right. Now, what we can see that these do not cares, I mean you can come up with a expression like this, and this can be a common term the way we had seen before, but it is better that if you have a combination of these and a combination of these, rather than individually going for, so because that will generate additional term. Could you get this? What I mean to say is that one option is this one, right, and this one, there are two ones, right, and then combining with this one, but that will require additional terms to be generated, right. So, this is the complexity of group of 4, this is the complexity of group of 4, and then a third term which is common, which is of course shared, but each one will require 3 terms. But in this case what we are having, these 2 terms are always required, and you are having only one term which is group of 4 with same complexity, that is only getting generated. Okay. So, here these do not care cases, we are simply ignoring them and we are going in the manner as it has been shown, and by which we are reaching a get count cost of 14 and total of 20. Okay. Now, let us look at little bit more complex thing, where the do not care cases are this one. Okay. Right. Okay. So, again there is a possibility of in the minimized expression having a group of this, right, similarly a group of this and a group of this. So, these are the possibilities, right, and if you compare all those possibilities, then you can see that considering this one and do not care over here and these do not care and one over here, you can generate a shared term, is not it. So, this term, this group is shared, and similarly we can generate between these two a shared term, and compared to individual minimization, the way we would have done in this case, as I repeat again, like this case, right, and over here to cover all these ones. Okay. Compared to that, if you weigh that realization of these two which is shared, realization of these two which is shared in this manner, okay, you will find that the relative cost is coming to, in the first place 18 get input cost, and total cost is 24, and if you try it individually, you can see it will go for larger value of 20 and 28. Okay. So, this is the different way for multiple output minimization using the cost criteria that we have defined. We can look into it and pick up the one which is favorable, and this was for 2 outputs. Similarly, you can go extend it for 3 outputs. I know this is more complex, but the concept remains the same. Okay. So, with this we come to the conclusion of this particular class. What we have discussed in briefly, we have seen that comparison of different logic circuit implementation can be done through defining certain cost criteria. We define literal cost, which is considers the number of times a variable appears in an expression, either in complemented or in uncomplemented form, and get input cost considers total number of inputs to different logic gates, and there is a definition related to total cost which considers get input cost as well as number of logic gates that are used, and consideration of shared terms in multiple functions, multiple output functions can lead to an overall minimized circuit with less cost, and do not care conditions can be useful in deciding shared terms that can be generated for minimized circuit. Thank you.